going to finish up what we need to do for chapter 10. Okay, so we're going to finish up our last topic, which is going to be on phase changes. Today will be relatively simple. I mean, and I know that's like the famous Brosnan saying, but I think today will be okay. You should be able to hang with it just fine. I will not take the entire hour to teach today, so we will have a little bit of time at the end of the hour so that you can get started on topic 3. Homework topic 3 will be due on Thursday. However, your test is going to be on Thursday as well, so we will review all day tomorrow. So I highly doubt we'll have a chance to grade topic 3 on Thursday. We might. I'm not anticipating this to be a full test. I'm still messing with it, but I think it's going to end up being more of like a quiz-ish. I mean, it's certainly going to be, I would say it's going to be at least a half hour long, but I'm not convinced it's going to be a full hour extravaganza on Thursday, okay? So this is our last one before the AP exam. Speaking of which, the AP exam is in, 19 days, if you don't want to count today. Just saying, like I've been saying. Speaking of which, what I want to show you, and I did show the people that showed up on Sunday this, but if you are looking for somewhere to start, and you're looking for something to do to study, okay, what you can do is you can use our online study book, okay? It's an e-book of something you could buy at Barnes & Noble's. It's a study book, okay? If you go to It's Learning, go to the home page, and go to this resource chunk, this OWL launch page. If you go there, you'll get this kind of sign-in for this Cengage Brain. Cengage is the company that publishes our textbook. If you log in with your account, you'll get to some launch page that looks like this, and you should be able to click on a link down here that's called SSO, FT5, K12, HS, AP exam, blah, 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 blah. It's a weird link, okay? This is the e-book of that study book that I was telling you about. It's called Fast Track to a 5, okay? Which sounds encouraging. And what it is essentially this study book has a diagnostic test, which is a AP test that you can take digitally, and it'll spit out basically what you could expect to get on the AP test based upon how you did, okay? It has topics, 13 different topics spread out over the course of this AP chemistry class with basically little snippets you can read, you can review, and then they have a little quiz at the end of each topic. So it kind of reviews the entire year, okay, broken apart into 13 sections. And then it has 2 practice tests as well, so there's 2 more AP exams at the very end of this practice book as well. Okay, the diagnostic test gives you a lot more information. The practice tests are just kind of there, and they give you some answers, and there's not much explanation, not much kind of in the way of raw score or how you did, I guess. Joe?
Is the diagnostic test the same test over and over?
Yeah, every time you take it, it's the same test. So it is one version of that test. You can't revisit and have a new diagnostic test. That would be sweet, but that's not the way it works. So it is just a single diagnostic test. If you click on it a second time, it's going to be the same thing. Okay? But anyway, so if you go into a topic, if you go to one of their chapters, okay, I think, no, come on. Okay. Apparently topic 2 works. If you click on a chapter, okay, it'll bring up a link, and you can click on that link, and then it'll bring up the PDF of that chapter. So I actually have the physical copy, the hard copy of this in my office. I don't have a class set. They just gave us access to the ebook, but I think it's something decent you can check out if you want to check out. So each chapter is between 10 and 25 pages. This looks like a longer one, okay? This is atomic structure and periodicity, so what we just did, I think, 2 chapters ago, okay? It's got all sorts of high points, AP tips, blah, blah, blah. It goes through all the content, the things you need to know, so on and so forth. And then you can go back and go over here and go to the quiz for that chapter. And you can start the quiz, and you can go through some multiple choice questions that relate to that quiz as well, or to that chapter, okay? So it's kind of a decent resource. I would encourage you to start there if you have not started. I think it's a good spot. Albert obviously has 1,400 questions. I would encourage you to be flipping through those during your leisure time. And nonetheless, there's 19 days, and if you want to do well, I would encourage you to start yesterday. Okay. If you catch my drift, if you haven't started, please start. Okay. Anyway, so that's how you can get to there. If you want to get to there, I would encourage you to do so. It's a good resource, and it's a good place to start studying it with the diagnostic test and things like that. Today, let's look at today's sheet. Again, this will go pretty quick. I don't think this will be too difficult for you to get. Hang with me and ask questions if you got some questions. We're starting at the top. These are the two textbook definitions of boiling point and melting point. Okay, so boiling point is defined as the point where vapor pressure of the substance and atmospheric pressure are equivalent. When those two are equal, your substance will start to boil. Okay, so the blanks here are for vapor pressure. That's fun. Oh yeah. Technical difficulties again. All right. So this is vapor pressure up here. Okay. The normal melting point, that definition is all sorts of weird. Okay, it just sounds messed up. You know what a melting point is. Obviously, it's the temperature at which your solid's going to turn into a liquid. They're defining it based upon vapor pressure. So essentially, if the vapor pressure of the solid and the vapor pressure of the liquid are equivalent, then you're at the melting point. Again, that seems just kind of, it's very indirect in my opinion. So that's what the textbook says. Yeah, that's all I really got to say about it. You can stare at it if you want, but I don't think that makes much sense. Not saying it's wrong, it's certainly correct, but it just is a weird way to think about it. Okay, let's look at this graph. This is a heating or cooling curve, or you could also call this a phase change diagram. Any of those work. Okay, you've seen these before, right? This is for water. If we were to heat up a sample of water, it would follow this curve. In other words, if we started way over here at negative 40, that'd be ice. We add some energy, we heat it up, we reach 0 degrees Celsius. What happens at 0 degrees Celsius with water, or ice rather? It's going to melt, okay? If we're adding energy, right, it's going to melt. If we're taking energy away, it's going to freeze. Both directions work. So we're melting. We reach right here, and now we are heating the water. We reach right here, and now we are at 100 degrees Celsius. And what happens to water at 100 degrees Celsius? It boils, or undergoing the vaporization phase change, so we're changing from liquid to gas. And we get over here with the very last incline, which is heating up steam. Okay, you've seen these before. Question 3 is asking you to put the phases on this graph. So down here, all we have is solid. On this plateau, we have both solid and liquid. That's melting. The big incline, we have just liquid. We're heating up our liquid sample. The next plateau, we have liquid and gas. And then last but not least, that very final incline, we have just gas. Okay. Now, number 4 says use intermolecular forces to describe what's happening along the flat spots of the graph. So we are adding energy. Okay, throughout this process, as you go further left to right on this graph, we're adding energy. So the question is what happens at those plateaus? Okay. All the energy being added is being added and used to break intermolecular forces. Okay? All the energy being added is being used to break those intermolecular forces, to change your solid to a liquid or your liquid to a gas. Okay? When there's an incline, when temperature increases, the energy being added is now being added to increase the kinetic energy of the molecules. Okay? It's making the molecules move faster. So the plateaus are phase changes. When you add energy, we're breaking intermolecular forces. The inclines are pure substances, either solid, liquid, or gas, and when you add energy, you're just increasing the kinetic energy of the molecules. Okay? A couple other things I want to point out on this graph that you can do or that you can figure out. Thing number 1 is you can figure out the specific heat capacity based upon the slope of those inclined areas. What I mean by that is, if we look right here, okay, the slope of that portion of the graph tells us what our specific heat capacity is for that substance. Okay? The units of a specific heat capacity are given in energy per mass divided by a temperature. In other words, common units of specific heat capacity are calories per gram times degree C. Okay, we probably use that more than any other one. Another one would be joules per gram times degree C. Okay? So if you look at the way we have our graph set up, the calories per gram is the x value, the temperature, or the degrees Celsius, is the y value. So in math class, you do rise over run to find the slope. But if we want the correct units for our specific heat capacity, we would have to do run over rise in this case, x over y. And that's just to get the units correct. That's why we would do it that way. Okay? So for example, if we looked at this slope, the middle slope here, we have a value of 100 calories per gram. Okay, and we would put that over our degree C. So we would have, we're going up by a value of 100 as well, so we'd have 100 degrees Celsius. So in other words, the specific heat capacity of liquid water is 1 calorie per gram times degree C, which hopefully sounds very familiar because that's exactly what we've been telling you since like 7th grade. Okay? So the specific heat capacity of water is 1 calorie per gram times degree C. Okay? So the slope you can use to find the specific heat. Okay? Another thing you can pull off this graph is what's called the heat or enthalpy of vaporization, or the heat or enthalpy of fusion. We've used these before. Okay? I think we talked about this earlier this year at least one day, and we certainly talked about it last year in regular chemistry. So the enthalpy of fusion and the enthalpy of vaporization. Okay? These describe the amount of heat that's required to undergo these phase changes. You can figure out these quantities from the graph as well. Here's the melting, or the fusion rather. How much energy did we add per gram? Well, we added, it looks like 80 calories per gram. So this can be pulled off of your graph as well. Okay, how about for vaporization? This is much bigger, obviously. But if you calculate all those little boxes, we have 540 calories per gram. Okay? So the two things you can really use these heating and cooling curves for, you can use the slope to figure out specific heat, and you can use the quantity of those plateaus to figure out these heat or enthalpies of fusion and vaporization. Okay? So this is 80, that's the fusion, that's the enthalpy of fusion. This is 540, that's vaporization, that's the enthalpy of vaporization. That's kind of how you can use these things.
Wait, what was that whole fusion?
Like, where was it?
Yeah.
Right here, the plateau.
Okay.
So fusion's when you're melting or freezing, right? Okay. So you can pick these values off these charts. Okay? Let's go to the next slide. We did number 5, by the way. That's literally what I just did. So how much energy did it take to break the attractive forces at 0? Well, it took 80 calories per gram. Okay, that was the plateau. How much did it take to break it at 100? Well, that was the 540 that we just solved for as well. And that's calories per gram. Okay. Now here's a good question. And this is a question that AP will ask in the context of this unit. Why does it take more energy to boil than it does to melt? Okay. Why is more energy required to boil a sample than it is to melt the exact same mass of that sample? What do you guys think? Well, we're increasing energy in both of them. Yeah, I can repeat the question. Why is more energy required to boil, or in other words, let me say it a different way. Why is more energy required to make a sample go from a liquid to a gas, undergo the liquid-gas phase change, than is required for the same sample to go from a solid to a liquid? It takes more energy to go from liquid to gas than from solid to liquid. Why? That's the question. Okay?
Because you're having to like completely correct the modes rather than just kind of like weakening them.
Yes, that's the correct answer. Okay, so we've got intermolecular forces, right? Okay, we have intermolecular forces. When we go from solid to liquid, we've got kind of everything's in a nice rigid spot in a solid. Okay, when we melt that, we turn it into a liquid, and now we're kind of, these things can move a little bit, right? There's still intermolecular attractive forces there. There's still these attractive forces holding it together, so it's a liquid. But we're breaking some of them, but we're certainly not breaking all of them. When we go from liquid to gas, we are breaking every single intermolecular force, because now our liquid, which is still attracted to each other, needs to turn into a gas, which is going to be highly separated with a lot of extra space in between. So from liquid to gas, we're breaking all of the intermolecular forces. Whereas from solid to liquid, we're just breaking some of them. Okay? So it takes a lot more energy to break all of them, obviously, than it would just some of them. And that's why it takes way more energy to boil something as opposed to melt something. Okay? Much easier to melt something than it is to boil something. Okay, let's keep going. At the bottom of this front page, I have a graph for you. That graph's going to help you answer question number 6. Question 6 says, at the top of Mount McKinley in Alaska, you boil some chicken soup because, you know, climbing mountains is tough work and you're hungry. Okay? And it's cold, probably, so. What better food than chicken soup on a cold mountaintop? Anyway, because you want it hot. You don't boil your soup? I get it to a boil and then I take it off the stove and it's good.
You make ramen hot. Have you ever made ramen noodles? You boil the
It's
water.
not soup.
If you haven't, are you going to college?
I got like
Ramen's awful. Anyway, so the question here in number 6 is, why is your soup boiling? Your soup's boiling at 78 degrees Celsius on the mountaintop. Okay, what would the atmospheric pressure be based upon that fact? Use the graph. That's my advice. Use the graph and use the definition of what boiling is. Those are the 2 pieces of information you need. Christian, what you got? Nope. It's around 300. Okay? How did they get that? You use the graph, right? So here's the definition of boiling. Here's the definition of boiling. Boiling is when the vapor pressure and the atmospheric pressure are equal. This graph is showing us temperature and vapor pressure. So if we trace over where the temp is 78, and we find out what the vapor pressure is, it's a little above 300, 300-ish. Okay? Well, if it's boiling, the vapor pressure and the atmospheric pressure have to be equal. That's the definition of boiling. So the atmospheric pressure at 78 degrees Celsius is going to be equal to the vapor pressure, and that's going to be 300. Okay? Or give or take 300. Oops. 325, whatever you want to call it. This is millimeters of mercury, by the way. Okay? I'm just going to say 300 because it's nice and round, but obviously it's probably a little above.
How do you know?
Okay. How do you know? Because I just said the definition of boiling. Okay? Why is the atmospheric pressure different at the top of Mount McKinley than in Wausau? Okay, why is there less atmospheric pressure on the top of the mountain than there is in Wausau? Bennett?
It's like less stuff above you.
There's less stuff above you pushing down, right? So the atmospheric pressure is the weight of the atmosphere pushing down on you, right? So if you're down at sea level, you have a whole bunch of atmosphere above you. If you're on top of a mountain, you've got a lot less atmosphere pushing down on you. It's kind of like when you're in a pool. You dunk your head under water, if you're a foot under the surface of the water, you don't really feel any extra pressure. But if you dive way down at the bottom of a 12-foot pool, your ears are probably not feeling too great, and you got to repressurize them, okay? So it's the same thing, right? The deeper you go in a pool, or the deeper you go in a lake, or wherever you're swimming in, okay, the more pressure you would feel of the water pushing down on you. It's the same thing with the atmosphere, okay? As you go higher in elevation, there's less atmosphere. As you go lower in elevation, there's more atmosphere pushing down, okay? On the back side, this is a phase diagram. Okay, this little chart on the right is a phase diagram. These things are used to help us figure out what phase a sample will exist in given a certain pressure and a certain temperature. They're very easy to read. Okay? So for example, let's say I said, hey, you have 1 atmosphere of pressure and the temperature is 50 degrees Celsius. What phase are you in? Well, we could find 1 atmosphere of pressure, trace it over until we hit around 50 degrees Celsius, and the point we're at is right here. That's in this region, therefore it is a liquid. Okay, that's how these things work. That's how these phase diagrams work. You get a pressure, you get a temperature, find where you are, and what phase are you in. They're really actually kind of cool, and they're really useful. Okay? Now, on these phase diagrams, there's 2 points that are kind of important. The first point is called the triple point. The triple point is the combination of pressure and temperature that will give you all three phases at the exact same time. Okay? So at this point right here, at a pressure of 0.006 atmospheres and a temperature of 0.0098 Celsius, water will exist as a solid, liquid, and a gas all at the same time. You can see it. Oops, now you can't. Control Shifty. So here's this guy. He's working on getting to the right spot. I'm going to fast forward it. If you notice, okay, in that petri dish now there is ice, there is liquid water, and it's bubbling. So it's boiling. This is the triple point of water. That's very exciting, actually, Christian. I'm sorry, I don't know if you're like skydiving on a regular basis or doing extreme sports, but that's exciting in my life. Okay, I think that's kind of cool. That's weird. Okay, that's weird, but it exists. So every substance has a triple point. No. So this would not happen in a natural setting, right? Because the pressure and temperature combination for the triple point is usually not even remotely close to what standard pressure and temperature are. So you have to really manipulate it, and they are. Okay, Bennett?
So if you put your hand in the boiling water, it wouldn't actually be hot?
No, it's not hot at all. It's just above 0 degrees Celsius. So the water is boiling, but it's not even hot at all. Yeah. So no, if again, and this is it would be kind of tough to do, but if you were in a chamber that you could lower the pressure, water boils at a lower temperature at low pressures, right? So if you could lower the pressure substantially, you could boil water at like room temperature. And no, it would not be hot because the temperature is just the temperature. It would still be 25 degrees C. It's just that lower pressure allows it to boil at a lower temperature. Which is kind of weird, yeah. Anyway. Okay, so that's the first point that I wanted to point out, I guess. Sorry for the pun. The critical point. The critical point is the temperature and pressure combination where above that, liquid and gas are indistinguishable from one another. Okay? In other words, if you have too high of pressure, extreme temperature, essentially liquid and gas are no longer distinguishable. And there's not a nice, well-defined line kind of separating them on our graph. I don't know what that looks like. Sounds kind of cool, but it's tough to visualize. I don't know what that even looks like. Because obviously at normal conditions, it's very obvious what's a liquid and what's a gas. So to reach a point where they're indistinguishable, I don't know. I don't know what that looks like. The last chunk of class that I'm going to teach you is a big practice problem. Okay? We have done these before. It's probably been a long time, but we have done these before. Question number 8 says, how much energy does it take to heat up a 45-gram sample of ice at a temperature of negative 13 degrees Celsius to steam at a temperature of 123 degrees Celsius? Okay? So we have a chunk of ice, 45 grams of it. We're going to heat it up. We're going to melt it. We're going to heat up the water. We're going to boil the water. We're going to heat up the steam. Okay? So if you're tracing along your heating curve, we're down here. We're going to heat it up. We're going to melt it. We're going to heat up the water. We're going to boil it. And we're going to heat up the steam. There's 5 chunks of this problem. Okay? There's 5 chunks of this problem. There's energy required to heat the ice. There's energy required to melt the ice. There's energy required to heat the water. There's energy required to boil the water. There's energy required to heat the steam. It's 5 separate equations that we add up to get the total amount of energy. Okay? So here's what we've got going on. Q equals MCAT. We know that equation. That describes the amount of heat added during a temperature change. Where on this graph is the temperature changing? What regions? The slopes, right? So there, hey, the temperature's changing. There's the temperature changing. There, the temperature's changing. You need Q equals MCAT for those 3 regions. The other 2 regions are phase changes. During phase changes, you need this equation. where Q equals m delta H. Delta H is either for fusion, melting, or for vaporization, boiling. Okay, so during the melting, the little plateau down here and the big plateau up here, you will use Q equals m delta H. And you will use a different delta H depending on what you're doing. Okay, you have a delta H of fusion, you have a delta H of vaporization. You also have different specific heat capacities. Ice, water, and steam do not have the same specific heat capacity. Okay, if you are heating ice, you need to use this specific heat capacity. If you're heating water, you need to use this one, and if you're heating steam, you need to use this one. Okay? So, it's been a while. Give it a shot. All right? I'll go through the answer in just a little bit here. But try this. It's been a while. It's been a while. What's up?
Would this be like one of the previous constants AP test where it's like
Are you recording anything?
Because Drew had asked me to.
Oh, yeah.
And I leaned into the microphone so that when he watches this, he knows we're talking about him.
Andrew, if you're listening to this, give me $1 tomorrow.
Christian wants $1, Drew. Anyway, so I'm going to go through this problem. Please follow along wherever you're at. Okay? This region down here I'm going to call Q1. Or not Q1. Now I'm going to call it Q1. This is Q2, the little plateau. This is going to be Q3 with the 3. This is Q4. And this is going to be Q5 way over here. Okay? So to solve for Q1, I need to use Q equals MCAT. My mass is 45 grams. My specific heat capacity of ice is 2.108 joules per gram times degrees C. And then last but not least, I have my change in temperature. I'm going from negative 13 up to 0. Final minus initial. So 0 minus negative 13 is a positive 13. My temperature change is 13. Follow that? Because we didn't start at negative 20. We started at negative 13. Okay? You plug this in. You get some value of joules. What do we get? I think it's 1,200 and something. Yeah, I'm going to worry about sig figs at the end. I'm not going to deal with them right in the middle. Okay, I'll deal with them at the end. So 1233 joules. Okay, for the first chunk. Q2, we are melting our 45 grams of ice. So we have 45 multiplied by the heat or the enthalpy of fusion, which is given to you up here, which is 330 joules per gram. You do this math and you get 14,000 and something. Thank you. 850 joules. Q3. We are now heating the water. Q equals MCAT's what we need. Mass is still 45. That hasn't changed and it won't change. The specific heat of water is different than ice. We need to use a different value, 4.184 joules per gram times degrees C, multiplied by our change in temperature. We're heating our water from 0 degrees Celsius up to 100 degrees Celsius. Change in temp is 100. Okay, you plug this in, you get 18,000 something?
18,820.
That's Q3. Q4 is the boiling. Okay, we need the enthalpy of vaporization. So Q equals M times delta H. M is still 45. Surprise, surprise. And the enthalpy of vaporization is given to us as 2260 joules per gram. Okay, which is going to give us a Q4 equal to 107,000.
101.
Oh, I'm sorry. 700. That's where my brain was thinking. Okay. 101,700 joules. Q5. We're heating up the steam. We need Q equals MCAT again. 45.0 grams multiplied by the specific heat capacity of steam, which is different. 1.996 joules per gram times degrees C. Change in temperature, we're going from 100 up to 123. So our difference there is 23. Q5 equals 2,000 something?
66.
2,066 joules. Okay, those are the 5 individual pieces of this problem. Once we get all the pieces, we just add them up to get the total energy. So Q1 plus Q2 plus Q3 plus Q4 plus Q5 is going to equal Q total. Okay? And we get a Q total of, I think, 139 kilojoules. Or you could say 139,000 joules, right? But that's our final answer. Okay? If you can do that, you're in good shape. That's all I've got on the phase change stuff. Okay? You should know how to look at those graphs, the heating and cooling graph, and the phase change graph, and how to use those things. Okay? And then you should be able to do this kind of math. But this math is pretty plug and chug, pretty simple. Okay. So I'm all done for the day. You can spend the last 18 minutes taking a peek at your topic 3 homework assignment, which is due on Thursday. If you need a textbook, let me know. I'll grab some.